Hey everyone, so today we're going to be doing a tutorial on how to do one-way analysis of variance with univariate ANOVA along with some post-hoc tests in R and RStudio. So let's get right down to it. So let's get into R right now, open it up, and here we are in R with our script that we've been working on previously. Now I'm going to modify this a little bit to what we've seen in the past because it's going to be a little bit easier on my eyes this way. So first of all, I'm going to actually take this window and move it over, squash it down, because I like to have a little bit more room to see what I'm doing on this side. The other thing I'm going to do is change the theme today. So if I select up in the top here, Tools, and go down to Global Options, and I look at Appearance, now I'm going to change my editor theme. I'm going to pick something like, at this point, something a little bit of a darker theme. For example, look here, I've got one called Twilight, or Tomorrow Night. That looks pretty good. Tomorrow Night 80s. It's got some funky colors in there, pastels. Let's put that in there for now. Now, it looks a little bit easier on my eyes here. It's going to be a little bit better for me to be following along and doing all this reading and staring at the screen the whole time. So we're going to be working with a data file called NHLsalaries, and that's just salaries of NHL players from the 2017, 18, and 19, and 20 seasons. And it's the top 10 players, their salaries in millions of dollars per season. So let's open up that file by importing the CSV file from text. It's called NHLsalaries.csv. Open that, and I'm going to call it just straight NHL.data. And it's got headings. And I look down, it looks pretty good here. I'm going to click on Import. You see we've got our player rank for each season, the name, and their salary in millions of dollars. So the next thing I want to do is load a couple of the libraries I'm going to need this time. And the ones I'm going to be using are car. We loaded that last time. And if you don't already have it, just do a quick install of car. The other one we're going to be using is called EM means, or estimated marginal means. If you don't have that one, go ahead and just click on install EM means. But I've got it installed already. I've clicked on the little button here, and it's loaded up that library for me. So I'm going to go back to my script file, and I'm going to start a new section. I'm going to do some of the things I've used before, such as attaching and detaching. So I'm going to select all of this at this point. In fact, I'll copy that as well and scroll down. I'm going to put it at the bottom of this, and I'm going to call this ANOVA univariate. Remember, this options will just make sure that it's not going to be writing out everything in scientific notation for me. And then I'm going to load up a data frame. And my data frame that I'm going to be using is NHL.data. I'm going to attach the data frame, and then I need to do a bunch of different stuff to it. So let's get rid of all of that into it. And think about what's the first thing we want to do. Why don't we have a look at the box plot of the data. So let's just do this really quick. So we can just type in box plot, and because I've attached it, it should work if I just type in salary. Now, let's highlight all of that and run it. We can see it's in behind me, it's created a single box plot of all of the salary data. That's not super useful because that is all 4 years grouped together or lumped together. So let's see if we can get something a little bit better than that. So let's do a secondary box plot. In fact, let's do a box plot, in this case, salary as a function of season. Now if I run this, what you see is now I have separate box plots, one for each year, 2017, 2018, 2019, and 2020. Okay, that's great. So that gives me an idea of what the data looks like. So the next thing we might want to do is create an ANOVA model. But before we do that, we might want to check whether or not our data in the season is represented as a factor or as a categorical variable. Because our data will come out differently if it's represented as scalar. So 2017, 18, 19, 20, it might think of them as numbers rather than categories. So one way we can check is just by typing the command levels NHL.data $ season. If I hit enter, what we see is it comes up as null. And what that means is there's no categories or no levels in that column. So one thing we may want to do is actually change that to a factor. Now we did that before, but I'm going to add that in here. In fact, I'm just going to put it at the top to remind us of how we did that. So what we're going to do is write right back into its own data file or its data frame, NHL.data $ season. Into that, I'm going to put as.factor, and then its same value, NHL.data $ season. Okay, now when I run that command, I'm going to hit Control Enter. What it's done is it's created levels for each of those values that are in that category, in that column. So 2017, 18, 19, 20 are now factors. So if I just run that command that I did before, arrow up arrow for levels on season, now we can see when I run an output, it gives us 2017, 18, 19, and 20. Okay, now that we've got that done, I can now create a model of our analysis of variance. The way we're going to do that is maybe by giving an object a name, NHL.model. And into that, I'm going to put a function called AOV, or analysis of variance. AOV, and it's very simple here. It's going to be salary as a function of season. Then what we'll do is we'll ask it to give us the output of that model, so NHL.model. And the other thing we could do is ask it for a summary of NHL.model. Okay, let's see what happens when we run all of these different commands. So I don't need that top one anymore. I'm just going to be running everything from there down. Okay, let's run that. Okay, so what it's done is it's done analysis of variance. I've gotten, when I just ask for the model, it gives me my sum of squares and my residuals and my degrees of freedom. So not a ton of information there. When I ask it for a summary of the model, it gives me the entire ANOVA table. So my season, that's degrees of freedom of 3, sum of squares of 37.62, and mean square of 12.54. My residuals, or my error term, has a degrees of freedom of 36, sum of squares of 88.18, and mean square of 2.449. And that gives me an F ratio of 5.12 and a probability of 0.00472. Right? Okay, so that's it for doing analysis of variance. But we could do a couple of different things to look at the differences between our different times. So, for example, we know that there's a difference somewhere in our data here. So we don't know if 2017 is different than 2018, or 2018 is different than 2020, or 2019 is different than everything. So we can do a test to ask it which is different than which. And the simple way to do that, or the first way that we're going to be doing that, is simply by doing a function called TwoKeyHSD. So TwoKeyHSD, and it's just going to be an NHL.model. And what that's going to do is run multiple comparisons of each year against each other year and use a TwoKeys correction to correct for the multiple comparisons and tell us which year is significantly different than which other year. So if I run the entire thing again, I'm going to give myself a split here just so I know. There, that's the chunk I need to run each time. Okay, so it's given us the whole set of data again, but down at the bottom, we can see I've got 2017 and 2018, gives me a difference and a p-value, and that's an adjusted p-value. And we can see that if we look down that whole list, the only one that's less than 0.05 is this second one, and it's this comparison between 2019 and 2017. So that's the only difference that's significant in this entire set. There's a few different other ways we can actually look for these differences if you wanted to do them. So, for example, we can use what's called, and this is why I asked you to load this package, EM means, and that's estimated marginal means. So EM means, and what we ask for is NHL.model, comma, and then I put pairwise function of season. And then I can add an adjustment factor. So if I go adjust equals TwoKey, that should give me the same thing as my TwoKeyHSD. So let's just run that. Trying to figure out why it was giving me an error there. I threw an extra M, so it's EM means, not EMM means. Okay, run that again. Okay, so this time we can see that it's given me my TwoKeyHSD output here and my contrasts here below when I run the EM means. It gives me not only the means, but it gives me the contrasts. So again, the only one that I see that is different, which is unsurprising because the other TwoKeys corrected, is 2017 to 2019, and the p-value is 0.022. And we can see that's the exact same values as I have here. And in fact, if you look at all of these values, they're going to be the same. But I can use different adjustment factors. So I can use a Bonferroni adjustment if I wanted. If I decided Bonferroni was a better way to go, and we just do that with Bonf. So if I run that, we can see I get a different adjustment factor. Now I've got P is 0024. Or I can use a adjustment factor of home. So that will give me another different type of adjustment. This one is 0.0024. It's the same as Bonferroni because it is actually the lowest value that we're going to get. But we see the other ones are adjusted slightly different. So there's a bunch of different correction factors that you can use, or adjustment factors. So you could use TwoKey, Bonferroni, home, as I suggested just a second ago, Sedac, Chefe, done it. It's actually done it X. Hochberg. What else do we have? There's other ones you can look up, but essentially there's a bunch of different adjustments that you could make, and here's a bunch of the different ones that you could put instead of adjust, home, or TwoKey, or Bonferroni. If we don't put adjust in here, it's going to default to using TwoKey adjustments. Okay. So what's the next thing we want to do? So we've done our pairwise comparisons, and we've done them in a couple of different ways. Well, the last thing we could do if we want to, we could do a quick test for Levene's test of equality of variances. The way we're going to do that is Levene test, and it will be salary as a function of season. If we run that at the bottom, again, I've spelled it wrong. It's Levene, Levene test. Run that. Okay. What we see is our probability is 0.8787. So no problem for test for homogeneity of variance, so that looks okay. Okay, great. The last thing I may want to do is I could do a test and determine whether or not we've got normally distributed data within each of the different categories. So one way to do that, because we have a bunch of different categories, is using the tapply function. So tapply, make sure I'm spelling things appropriately this time. And I'm going to go salary this time, comma, season, comma, what I want to use here is Shapiro.test. Okay, so what that's going to do is apply a Shapiro normality test to salary as a function of season. Now, if I run all of that, you can see I've got all these normality tests now. Shapiro-Wilk for 2017 is going to show me that my p-value is 0.08, close but not bad. 2018, 0.104, 2019, 0.44, and 2020, oh, there we go. There's a bit of a problem there, 0.002. So one thing we could do is we could just have a quick look at our model. So remember we did MF row par MF row equals C2, 2. And what that will let me do is create multiple graphs within my little subset here. And then I'm going to plot NHL.model. I'm just going to see if there's anything stands out. What we see is, it looks here that I don't seem to have much in terms of residuals versus fitted. I don't see anything really out of the ordinary. My normal QQ plot shows a couple of outliers, 0.1 and 0.21. But again, those are really not that far. Point number 1 is actually the first value, which is the highest paid player in 2020. So because of that, that outlier might be causing our problem with normality. But remember that ANOVAs are relatively robust to mild violations of the assumptions. So because we've got really small data set here, we may not want to do things like transform or remove data points. One thing we might say is we're only going to accept our significance if it falls less than p equals 0.01, in which case it still does, and we should be fairly confident that our results are significant and they are actually valid in this case. Okay, so hopefully that gives you a good idea of how to run univariate ANOVAs and a few different post-hoc tests in R for a simple data set.